going to finish up the last part here of chapter 14, and we're going to roll into 15. Hopefully, make a pretty good dent into it. So, we've been talking about titrations, and we did experiment with some indicators as well. And we've talked about sort of how indicators work. So, remember, indicators are sort of like weak acids, and they have a protonated form where they have the hydrogen, and a deprotonated form where they do not have the hydrogen. And depending on sort of the ratio of those forms in the solution as to sort of what color you'll see, again, if sort of greater than 10, you'll see the acid color. If it's less than, then you'll see more of the base color. And a reminder again that they do work over a specific pH range, and typically they'll start to change color as they move along a certain pH range. Here's a big list of a bunch of indicators, and as you can see, crystal violet here, more of an acidic sort of indicator as it goes from kind of almost like the one we use in lab. It went from like yellow to green to blue. And then obviously here's our favorite one ever, which is phenolphthalein, right? Which works again between that pH of 8.3 and 10. And obviously colorless there in that sort of 8.3 range. It gets very light color along the way. So obviously you do want to pick a indicator that would really change color near your equivalence point. And as we talked about a few different types of titrations, you should know that at the equivalence point, again, of a strong acid, strong base titration, that's going to be a pH of 7. If you're doing a weak acid with a strong base, that should have a pH that's going to be basic. So you would want to choose one of those. And obviously, if you're doing a weak base with a strong acid, that will have a more acidic pH there at the equivalence point. You could actually do a calculation, and if you're doing a particular titration, and calculate your theoretical pH at your equivalence point and really pick an indicator that should work really well for you. So clearly, if we were doing the titrations like we did in class, this guy is not going to be really great for us for most of the titrations, again, because it's going to way change color too early for us to obviously know. The purpose, obviously, of the indicator is to tell us basically to stop our titration right near the equivalence point where the moles of the acid and the moles of the base will equal each other. All right, let's see here. It woke up maybe. All right, so there we go. So for this particular one here, let's see, move it up here so we can see it. All right, so if we were doing this titration of HNO2 with KOH, and we have this list of indicators here, and again, kind of shows you the color and acidic and their basic range of the indicator. Which one would be a good choice? So as we've been talking about, we do want to kind of think about the type of titration we're doing. HNO2, I know, is a weak acid. Once again, because it's not one of those 6 that are strong. So even without the Ka value being given to us, we know that should be a weak acid. KOH is definitely a strong base. And this is going to be a titration that's going to look something like this, where at the equivalence point, we are going to be basic in this case. We're going to be basic because we're going to have a salt that came from a weak acid that will go through hydrolysis and react with water and produce hydroxide. So what that means is in terms of choosing an indicator, clearly probably none of these are going to be all that great there since they're obviously going to turn way before we need it to turn. That gets a little bit into basic, but not very far. So again, probably the color change is going to occur by the time you get to the end of that. So really our choices here would be probably our last 2 would be a good choice as they definitely get it well into kind of the basic range there. And again, that's phenolphthalein and creosol red in this case. Any questions on how to choose an indicator? Yeah. Okay. Like you did in the titration the other day or last week, you actually used 2 different indicators, one for the earlier equivalence point and then one for the later equivalence point as well. And it gave you some nice colors, I guess, as you went through it. All right, that wraps up this chapter. Didn't have very far to go on that one there. All right, so the next that we're going to talk about is chapter 15. And chapter 15 is the rest of the stuff that gives people sometimes a really hard time. We're going to talk about two other types of equilibrium constants. We're going to talk about KSP, which is basically the equilibrium constant for things that are insoluble. And we're going to talk about KF, which is basically the equilibrium constant for complex ions. So these are two additional Ks that we could add to our ever-growing list of Ks: KW, Ka, B, C, P, all this kind of stuff, S, P, F. We'll just keep going. All right, so the first thing we're going to talk about is actually KSP. And we could have something that is insoluble like this salt here, silver chloride. And if you remember your solubility rules, and you remember group one that we did in the experiment, right? Chloride is soluble in everything except for three exceptions, which is group one of qualitative analysis, and that is silver, lead 2, and mercury 1 are the exceptions. So even though solubility rules tell us that silver chloride is going to be a solid and it's going to be insoluble. Even things that are technically insoluble will have some degree of solubility, which means even something like silver chloride will actually set up an equilibrium in solution. And it will look something like this. We have our solid silver chloride, and it will break apart into our ions. And because it will set up this equilibrium, we can write, of course, an equilibrium expression for it, which is known as KSP. In this case, it's going to be just like any other equilibrium expression, products over reactants. And here we have a solid, so we're not going to include it in the equilibrium here. KSP does stand for the solubility product. It is, as I mentioned a second ago, the equilibrium constant for things that are basically insoluble. So these are things that you would normally find, for example, on your solubility rules that say, hey, you're going to make a solid. One of the things about KSP expressions is it is typically always just the products involved. And that is because when you write these reactions, they're always written in this form. You have your solid on the reactant side, and you have your aqueous ions on the product side. So when you write a KSP expression, it pretty much is only going to be your products that are going to be involved because you should have pretty much a solid there on the reactant side. Just like any other equilibrium expression, we will still use the coefficients as the exponents. So if you have something like magnesium fluoride, it will break apart into magnesium ion and two fluoride ions. So we again do need to take the two into account, just like a normal equilibrium expression. Here, silver carbonate got two for the silver. Also, there are even here calcium phosphate, where they both have obviously some coefficients. So these are essentially, like I said, equilibrium constants for things that are insoluble. And we can actually use our friend Q that we saw in an earlier chapter to help us determine whether or not, for example, a solid will form. How do you calculate Q? Well, Q is still calculated the same as, in this case, the KSP. So you calculated the exact same thing. And just like it told us when we were talking about just regular equilibrium, are we at equilibrium or not? This will tell us whether or not we would expect a solid to form. And if Q is less than KSP, you have a unsaturated solution. And just like when we did it earlier, if you go in the opposite way that thing is pointing, that is to this side of the equation, which is aqueous ions, and you would not expect a precipitate to form, and you will have an unsaturated solution, right? An unsaturated solution is a solution that basically will continue to dissolve solute. If you calculate Q and it does equal KSP, you have a saturated solution. A saturated solution is a solution where you have hit at that temperature the maximum amount of solid that will dissolve. If you continue to add solid, you're going to get some stuff that will not dissolve. If you calculate Q and it's actually greater than the KSP, it's going to go opposite of where it's pointing, which means it's going to go towards the solid side of the equation. And you would expect a precipitate to form. You will have a supersaturated solution, which basically means all the solid is going to come out of solution, or most of the solid is going to start to come out of solution, and a precipitate will form. So we will see Q in this chapter. We will also talk about a few things that, again, sometimes people think when they kind of read those solubility rules that they're 100% always the case, and it's not really always the case. Solubility is affected by a lot of factors. We're going to talk about three really important factors through this chapter: concentration, pH, and common ion. These are things that will affect the solubility, as to, for example, whether or not you may actually see a solid form or not form, depending on some of these other factors. These are obviously some KSP values that you should memorize. No, I'm just kidding. But one of the things you'll look at if you look at your table, which is similar to this table, is they are very, very small numbers. So typically speaking, KSP values are really, really small numbers. And because these reactions are always solid to ions, which are aqueous, right, versus solid, because they have a really small KSP value or a small equilibrium value, we know that that means that mainly at equilibrium, we will have reactants. And that is why we consider these things to be insoluble, because under normal conditions, we pretty much got everybody staying there on the reactant side, which is the solid, and not breaking apart all that much. So you typically will find very, very small values for KSP. And that, again, is because pretty much most everything on this list is insoluble or slightly soluble, not very soluble along the way. You may have to, for certain problems, reference a table that's in your book for KSP sort of values, as they may not be given to you in a problem or something like that. We're going to talk about solubility and how to calculate solubility using our KSP. And there are two types of solubility that we typically sort of look at or sort of calculate. One is what is referred to as the molar solubility. And the molar solubility is the number of moles of solute that will dissolve in a liter solution. It is a fancy way of saying the molarity, basically, is really what you're looking for there. So when you solve for the molar solubility, you're solving for the concentration, basically, of ions that will dissolve in solution. And there is regular old run-of-the-mill solubility there, which is given in grams per liter. And if you think about the conversion between those, if you have solubility in grams per liter, or molar solubility, which is moles per liter, the thing that ties these together to do the conversion, right, is a little molar mass, right? Grams per mole. So that is the thing that sort of ties those two things together if you need to go one way or the other to figure it out. There, frankly, is sort of two types of KSP type problems or solubility type problems that you come across. One is they will give you the solubility of the compound, and they will ask you to calculate the KSP for that compound. And in that situation, what you would do is take the molar solubility usually, and you will then convert it into the ions concentrations. And once you have the ions concentrations, you basically could go into the equilibrium expression and really just solve for the equilibrium constant. The other way is they just straight up give you the KSP and that's it, and just ask you what is the solubility of it. And sometimes they may not even give you the KSP. Let's go look it up. They'll just ask, what is the solubility of this compound in water, basically, and is it moles per liter or grams per liter? In that particular case, an ice table is probably preferable to do the calculation. For the top one, you really don't necessarily have to do an ice table if you understand molarity, concentration, and how the ions concentrations are related to the whole thing. If not, I would also recommend maybe doing an ice table, because frankly, people screw up on the very small things in this chapter, which is sometimes they're like, well, I already minused it by 2. Do I still need to square it? Or I squared it, I don't need to multiply it by 2, or and those type of things. So sometimes even on a top part there where you might not actually need to do an ice table, still probably a good idea just to do it, just to visually see what's going on along the way. So that's a lot of words. Let's do one together here. the solubility of silver phosphate with a dramatic pause between the formula there. At 25 degrees is 1.6 times 10 to the minus 5 moles per liter. What is the KSP in this case? So we're looking for the KSP. And if you are not familiar with solubility rules for this chapter, well, frankly, you'll probably be okay, to be honest with you. So if you're asked what is the KSP or they give you a KSP, it's a pretty good chance that thing's a solid. Yeah, so this is just a good way to remember it. So we want to write really our salt here and how it's going to break apart. So this is silver phosphate, and it's going to be a solid. It is going to dissociate into its ions, which is going to give me 3 silver ions and a phosphate ion when it goes for a little swim. Now, in this situation, I could write my KSP expression for this, which is going to be my products, which in this case is my silver. And I do need a cubit because of the 3 that is there, times my phosphate, which obviously the coefficient there is 1, so I don't have to do anything with it. And really the goal here is to figure out in this problem sort of what is the KSP value. Now, like I said before, you don't necessarily have to do an ice table on this particular type of problem, but I'm going to show you the ice table so you can kind of see some of the differences maybe than what we normally would do in an ice table or have done previously. So if we were going to do an ice table here, we would start with our initial. And like normal, we're not even going to worry about our solid there on the left-hand side, right? Because it's not included. So just going to ignore it. We're just going to start with 0 because frankly, what was sort of given to us in this particular case. Um, And our change in this case is going to be +3. And what we typically use in this particular case, instead of the letter X, which if you want to still use X, you can, but people typically use when they're doing KSP the letter S. And the letter S stands for the molar solubility, which again is basically the molarity. So if you want to still use X, you can, but you can use S as well. And this would be plus S. Now, when we get down here to equilibrium, we basically have 3S and S in this case, right? Now, just like normal, you could put this into our expression, and that would give you 3S that's going to be cubed. And that is going to also be times by S in this case, right? So obviously here we can't solve for S because we don't know what the KSP is, but they did give us the molar solubility of this compound. And that is basically what S is in this case. Times 10, I think was to the -5 molar. So really at this point, what we can do is just put in our number. We're going to have 3 times our 1.6 times 10 to the -5, and we're going to cube it. And we're going to times it by 1.6 times 10 to the -5. And if we do that there, we can go 3 times 1.6 to the -5 and cube it. And times at 1.6 to the -5. That is going to give us a KSP of 1.8 times 10 to the -18 in this case. First off, any questions on the ice table? Yeah. Yeah, it is it's still an ice table. Pretty much all of it's the same thing, right? So there's slightly different things that happen with this, but it's the same idea, basically. Yeah. Other questions? Okay. Now, like I said, you really, for example, don't necessarily have to do an ice table in this particular case. Again, if you understand sort of how things, whoops, wrong way, come back this way, how things sort of relate to each other. So it is essentially doing the same thing as the ice table. Let's get rid of this here. So if you remember from concentration and talking about solutions, maybe from 200A, If you know the concentration of this guy, which is 1 times 10 to the minus 5 molar, it is a 1 to 3 relationship between that and the silver. So you could just multiply that by 1.6 times 10 to the minus 5 to get the proper concentration here of our silver in that solution. And obviously that's going to give you 4.8 times 10, whatever it is there, 1, 2, 3, 4, 5 minus 5. And it is a 1-to-1 relationship between those two, which means you take 1 times 1.6 times 10 to the minus 5. And that's going to be 1.6 times 10 to the minus 5. You then could just pop those guys right in there, right? And you're going to get the same answer. Now, the reason I say maybe still do an ice table is I can't tell you how many people will, again, forget that part of it and just cube it, right? Or do this part and forget to cube it. So again, sometimes just doing the ice table, even on this one, where you maybe don't have to if you understand how ions concentrations relate to the whole thing, and you kind of just go into it, is still probably a little bit more helpful, just so you don't kind of make those little mistakes. Any questions on that there? Yeah. So why don't you try one here? What is the solubility of silver chloride in grams per liter? So give it a go, see what you come up with. I'm thinking you might need an ice table on this one, perhaps. And let me give you some numbers from the periodic table. Silver, I think it's 107.9, and chlorine is 3545. All right, so take a few moments there to see what you come up with here. Okay, so let's take a look. So again, we're looking for the solubility here. We do have the KSP given to us. We're going to start with really our guy breaking apart here. So we got some solid silver chloride. We'll dissociate into its ions in solution. So a silver and a chloride ion. That's going to give us a KSP expression here. That's going to be the concentration of silver times the concentration of chloride, and that will equal our KSP value right there. Once again, not much to work with here, so we can safely assume we got nothing going on initially. Our change is going to be minus plus x and plus x in this case. We will end up here with basically x and x, or I guess I could use s there. See that even now, you guys started using that wrong one. I'll pop some s's in there. Plus S and plus S and S and S. Any questions on the table there? At this point, like normal, we're going to go into our expression, and that's going to give us S times S is equal to 1.6 times 10 to the minus 10. That is S squared is equal to 1.6 times 10 to the minus 10. That means we're going to do a little square root action there on both sides, and that's going to get us here the square root of 1.6 to the minus 10. It's going to get us a 1.26 times 10. Looks like 1, 2, 3, 4, 5 minus 5 will equal our molar solubility in this case. So this is the molarity here, as that is what S stands for. Now, that S is obviously the S in our tables. And by the way, that S is always the whole thing together as well. So that is also the molar solubility of the entire thing. Because again, if you have this guy, it is a 1-to-1 relationship backwards, right? So it's going to be the same thing as you go back that way. So we basically have 1.26 times 10 to the minus 5 moles per liter of silver chloride that we could get to dissolve. If we want to know what it is in grams per liter, we need a little molar mass action. So we're going to add those guys together. 107, try again, 107.9 plus 35.45. Going to be 143.35 grams per mole from the periodic table. That's going to be a conversion factor there. We're going to go 143.35 grams per mole of silver chloride. Moles are going to cancel. So 143 times 1.26 to the minus 5, going to give you a whopping 0.0018 grams per liter is the solubility of silver chloride in water, basically. Is that a lot? That is not a lot. You basically can take 0.002 grams of silver chloride and get it to dissolve in 1,000 milliliters of water. That is why we normally consider silver chloride to be insoluble, right? Because you cannot get a lot of it to dissolve under normal conditions. Question on that. Okay, we're going to continue on, like I said. So we're going to continue talking about this chapter. It's not a very big chapter, so do you want to make a good dent into it? So, any questions so far? All right, let's take a look at another one here. For this one, we want to calculate the aluminum 3 in a saturated solution of aluminum hydroxide. The KSP is 2 times 10 to the minus 32. So once you give it a go there, calculate what is the aluminum concentration here in this solution. The KSP given to us. So again, we could assume obviously this is going to be a solid. So we could set up our sort of equation here, which showing the dissociation into its ions, which will give us an aluminum and 3 hydroxides in this case. That's going to give us a KSP expression of aluminum concentration times the hydroxide concentration. And again, we do need to cube it because of the coefficient there. And that is going to equal 2 times 10 to the minus 32. Setting up our ice table here, we can go 0 and 0. Change going to be plus S plus 3S again, also because of the coefficient. Going to give us at equilibrium S and 3S in this case. Any questions on the table here? Like normal, we're going to go into our expression. So that's going to give us S times 3S cubed is equal to 2 times 10 to the minus 32. That is going to get us a 27S to the fourth is equal to 2 times 10 to the minus 32. I will be honest with you, most people forget to actually cube the number that's in there as well. They just kind of do the letter, so don't forget to actually do the number as well. I'm going to divide by 27. Then I'm going to actually take the fourth root of it there. Yes. And after I do that, I'm going to take 2 to the minus 32 divided by 27. Going to take my fourth root of it. And that's going to give me an S of about, we'll call it 5.2 times 10 to the minus 9 as my molar solubility in this case. If you're not sure how to do the fourth root on your calculator, you can use like your caret, a parentheses 1 divided by 4 will do it for you if you need. Or some people might have a sort of root button on your calculator that you could do that as well. So you need to do the cube root 1 divided by 3, square root 1 divided by 2, however you want to do it. And if you need to punch it in there along the way. First off, any questions on that there? That obviously, as we can see, is the concentration of aluminum because from the table it equals S right there. And that would give us our 5.2 times 10 to the minus 9 molar. Now, it didn't ask in this particular example, but if we wanted the hydroxide concentration, it is not S in this case, it is 3 times S. So if you wanted the hydroxide concentration, it would be 3 times our 5.2 times 10 to the minus 9 molar. And that would get us 3 times 5.2 to the minus 9. We'll call it 1.6 times 10 to the minus 8 molar would be our hydroxide concentration. Now, why would you maybe want the hydroxide concentration? Well, maybe you're actually interested in the pH of this solution, what it might be. And if you wanted to calculate the pH, now you know the actual hydroxide concentration, and that would allow you to calculate, obviously, our pOH, which would be minus the log of 1.6 times 10 to the minus 8. And that would get us a pOH of about 7.81, to which our pH would be 14 minus that. And in this particular solution is rolling with a 6.19 pH in this particular case. Any questions on that? So another aspect of KSP is if you maybe figure out the H plus concentration or OH minus concentration, you could also figure out the pH of that particular solution that's sitting there. And that would be something like aluminum, which is amphoteric. It could act as an acid or a base in this case. Yeah. Any questions on that there? The next thing we're going to talk about is using KSP values directly to figure out solubility of something or to compare maybe two substances, which one would be more soluble than another. For example, if you look at these three salts here, which is silver iodide, copper 1 iodide, and calcium sulfate, every single one of these guys, when they break apart, this guy breaks apart into a silver ion and an iodide. Our copper 1 iodide breaks apart into a copper 1 and an iodide. And our calcium sulfate here is going to break apart into a calcium ion and a sulfate ion. Now, if you want to use the KSP values directly to compare the solubilities of each of these, you can do so. And you can do so for one reason. Every one of these breaks apart into two ions. Yeah. So every one of them is breaking apart into two ions. And because they all break apart into two ions, the same number of ions in this case, doesn't necessarily have to be two, but they all break apart into the same number of ions. You can directly use the KSP values to help you decide which one should be more soluble and which one should be less soluble. In this case, the calcium sulfate would be more soluble because it has a larger KSP value versus silver iodide, which has a smaller one. Again, remember that all of these reactions are written solid to aqueous ions. And if you have a large K value in general or a large KSP value, that means when you reach equilibrium, you're going to have mainly products, right? And on the product side here is the aqueous ions, which makes them more soluble. So there is a limited situation where you can use the KSP values directly to predict which one's going to be more soluble or not. This is also very helpful when you're doing something like selective precipitation. And maybe you have two ions floating around in a solution and you want to figure out which one will come out first. And you can use the KSP values to help you determine that. Now, what happens if you're comparing something like these guys here, copper 2 sulfide, silver sulfide, and bismuth 3 sulfide? This guy breaks apart into two ions. When he breaks apart, this guy, you got three ions. And this guy here, you got a bunch of ions here, maybe about five of them. And in this particular case, they do not break apart into the same number of ions, which means in this case, you actually cannot directly use the KSP values to figure out which one's going to be more soluble. For example, if you looked up the KSP values for these guys, you would see in this particular case that our minus 45 here is the larger KSP value. This would be the smaller KSP value. And basically what that would tell you in that case is you would think that this guy's going to be more soluble because of that. And the truth is when you actually do the calculation, this guy is not more soluble. It's actually the guy on the bottom with the smallest KSP value. And that's because in this case, you cannot compare these guys because they do not break apart into the same number of ions. So if they do not break apart into the same number of ions, you actually have to do a calculation like we just did previously to figure out the solubility of everybody and then compare them. You cannot go directly by the KSP value. But if they do break apart into the same number of ions, you can use the KSP value to determine which one is going to be more soluble or less soluble. Any questions on that? So cannot use it in this situation, would have to calculate the values. All right, so as I mentioned earlier, there are certain things that affect the solubility of something. And one major thing that has an effect on the solubility of a compound is the common ion effect. And we talked about the common ion effect with buffers. And what we saw with weak acids and weak bases was if you have a common ion, it's going to cause the weak acid or weak base basically to stay together and not break apart because of our friend Le Chatelier's principle. It's going to push it all back together. Now, a similar thing happens with salts. When you have a common ion present, it decreases the solubility of that salt for the exact same reason. If you have a solid on the left-hand side of the arrow, and again, our aqueous ions on the right-hand side. The only place in this reaction where you can have a common ion is on the product side, which means if you have a common ion on the product side, Le Chatelier's principle is going to tell us it's going to shift away from that side, and it's going to cause your salt to basically come back together and stay together. It's going to keep it together, and that will decrease the solubility. So if we take a look at an example of silver bromide here, in water. So if we take a look at the solubility of silver bromide in just water, it's going to break apart into a silver ion and a bromide ion. Our KSP here obviously going to be our silver times our bromide, and that's going to equal 7.7 times 10 to the minus 13. Putting in our ice table here, 0 and 0, change minus x, s, plus s. There we go. Plus s and plus s. That's going to give us at equilibrium s and s. Put in our numbers in there. That's going to give us basically s squared is equal to 7.7 times 10 to the minus 13. And at this point, we will square root both sides. And after you do that, you're going to get a molar solubility of silver bromide in water of 7.7 minus 13. And we'll call it 8.8. Come here, 8.8 times 10 to the minus 7 moles per liter is our silver bromide solubility here in water. If we want to know what that is in grams per liter, we'll take 107.9, which is silver's molar mass, and 79.90, which is bromine's, and we will times it by 187.8. And that means in sort of water here, we can get a solubility of silver bromide of about 1.7 times 10 to the minus 4 grams per liter. So this is the solubility in grams per liter. This is the molar solubility of silver bromide in water. Now, what would be the solubility of our silver bromide when we were put it in a solution of 0.001 molar sodium bromide? So let's see how that all changes. So if we take a look at our silver bromide here, it's going to set up our equilibrium. And now we're in a solution of 0.001 sodium bromide. How that affects our ice table is initially we have 0 of this, but because we now have our sodium bromide, which is obviously a salt that's going to break apart into a sodium ion and a bromide ion, that being our common ion here, we do have an initial concentration here of our bromide from the silver bromide that's in the solution with it. So that is coming from our sodium bromide in the solution with it. The rest of the table will be the same, plus S and plus S. And this is going to give us S here and 0.001 plus S. Any questions on that so far? Just like normal, we're going to put this into our expression. And if we do that there for our common ion situation, we will end up with S times 0.001 plus S is equal to our 7.7 to the minus 13, which is the KSP for it. Now, just like we've done before with equilibrium problems, that K value there is a small value, right? And when we have a small value, we could do a little assumption, right? And assume in this case, S is going to equal 0. So we could actually do the exact same thing we've done previously. And that's going to make this much more manageable in terms of solving. And we're obviously going to get rid of just this S right here, which is what we're going to add it to. That's going to give us 7.7 times 10 to the minus 13. We're going to divide this to the other side, and we will end up with 7.7 to the minus 13 divided by 0.001. That is going to give us a molar solubility of 7.7 times 10 to the minus 10 moles per liter for silver bromide in this situation. We could also multiply it by the molar mass we calculated earlier, 187.8 grams per mole. And that's going to get us here about 1.4 times 10 to the minus 7 grams per liter in this case. First off, any questions on that calculation? What do we see here? Which one is it more soluble in? It is more soluble in water, yeah? Smaller negative exponent, larger number, right? So it is more soluble in water. And that is because of the common ion effect. So Le Chatelier's principle basically says we added more of this, going to cause the equilibrium to shift to the left. And that's going to keep it together and not make it as soluble. So the effect of the common ion, as you can see here, is the presence of a common ion typically will lower the solubility of that salt. It will keep it together because it's basically pushing it back to the reactant side and not to the product side. Any questions on that there? No. By the way, you can see silver bromide is even less soluble than I think silver chloride was. Right. All right. Let's take a look at one here. So why don't you give this one a go? What is the solubility? We'll do the molar solubility of silver chromate in a solution of potassium chromate and calculate it up. So we'll just do the molar solubility. That's good. Okay, let's take a look. So once again here, we're going to break this up into its ions. And in this particular case, we're going to get a couple of silvers, looks like, and a chromate. That's going to give us a KSP expression here of our silver, and we do need to square it because it's coefficient times our chromate. And that is equal, obviously, to our KSP that was given to us. Now, in this particular case, we also have potassium chromate in that solution, which is this. And because that is a salt, it will break apart into 2 potassiums and a chromate. And since the concentration of the whole thing is 0.1 molar, it is a 1-to-1 relationship between the whole thing and the chromate. And that means that the concentration of the chromate in that case will also be 0.1 molar. If you wanted potassium's concentration, you would have to multiply by 2, but we don't really need it in this particular problem. That is going to be our common ion that we see here. So it's important, just like almost you're doing buffers, that you make sure you do have, obviously, the initial there. Otherwise, obviously, you're not doing the common ion part of the problem. Chain's going to be plus 2s and an s plus s. And at equilibrium here, we're going to have 2s and 0.1 plus s. Any questions on that so far? We're going to go into our expressions. So that's going to be a 2s squared, a 0.1 plus s is equal to 9 times 10 to the minus 12. Once again, small KSP value, we could assume s is equal to 0 in this case. And once again, it is going to be the s that you're going to, in most cases, add to a number in this case. That is going to give us 4s squared times 0.1 is equal to 9 times 10 to the minus 12. However you want to do it. Take 4 times 0.1 gets you 0.14, and take 9 to the minus 12 divided by that. And that's going to give us an s squared is equal to 2.25 times 10 to the minus 11. So again, I multiplied these two numbers together and then divided it over here. Take in our square root. Going to give us an s of 4.7 times 10 to the minus 6 molar, which will be our molar solubility here of silver chromate. Should you check it, your assumption in this case? The answer is really you should. But to be truthfully honest with you, especially with KSP, because they're so small, usually you're in good shape. You don't usually have to worry too much about checking it. But if you did check the assumption the same way we would check a x is equal to 0 sort of assumption, and you'd be okay in this case. Any questions about there? All right. All right. So obviously, though, in this case, just to remind you, if you were interested in the chromate, you would have to put that S value in there. And if you were interested in the silver, you would put it into there. But again, when it comes back to the whole thing, it does relate to it. Any questions on common ion effect here? So that is one thing that can affect the solubility of a compound. Another really important thing that can affect the solubility of a compound, especially, is pH. And pH has a big effect on it. That's why on like that qualitative analysis experiment we did, and we got one coming up, I think, after spring break, a lot of the procedures do have you kind of like, make it acidic dissolution, make it basic, and so forth. And as we talked about, the purposes of that is allow you to keep certain ions in solution and allow the right environment for other ones to sort of precipitate out. So the presence of that common ion, as we just saw, does decrease the solubility. If you do have an insoluble base, it will dissolve in an acidic solution. And if you have an insoluble acid, it will dissolve in a basic solution. So if we take a look at our friend here, magnesium hydroxide, and the KSP for it is 1.2 times 10 to the minus 11. If we just run through our normal sort of ice table on this here, that we're going to end up with to look at its solubility here in water. Initially 0 and 0, change plus s and plus 2s. That means at equilibrium, s and 2s. This goes into our expression right there, which gives us s times 2s squared is equal to 1.2 times 10 to the minus 11. Once again, cleaning up this side, 4s cubed equals 1.2 times 10 to the minus 11. We're going to divide by 4 and take the cube root of it. So 1.2 to the minus 11 divided by 4. And then take the cube root of it. Again, if you don't have a root type of button, do a caret to the 1 divided by 3. And that should do that for you. That is going to give us a S value here of 1.44 times 10 to the minus 4. Remember here, we are kind of interested in pH. So if we take a look at our table, we can see that the hydroxide is equal to 2 times S. So the hydroxide concentration in this case is 2 times our S value of 1.44 times 10 to the minus 4. and that's going to give us a hydroxide concentration of roughly 2.88 times 10 to the minus 4 molar. That's going to allow us to calculate, like we did on the previous one, the pOH of this solution. And if we do that minus the log of our answer, we end up with a pOH of about 3.54. And that tells us that this solution's actual pH here is 14 minus that. That is a 10.46 pH. So this solution here, sitting in water or dissolved in water, has an opening pH basically of 10.46. So what does this mean? This means is if I decided to drop the pH to lower than 10.46, what will happen in this situation? The way I could lower a pH is to add an acid or a base. You would probably be adding a acid, right? And if you add an acid, you're essentially adding H plus to this equilibrium, right? And if I add H plus to this equilibrium, there is no H plus in the equilibrium, but there is some hydroxide in the equilibrium. And H plus and hydroxide will come together to make our friend water, right? And that is essentially going to remove the hydroxide from this equilibrium. And when it removes the hydroxide from this equilibrium, which I think was like something you maybe did in one of those labs earlier on, that's going to cause, based on Le Chatelier's principle, the equilibrium to shift to the right. And when the equilibrium shifts to the right, that is aqueous ions all day, and that's going to increase the solubility of this, and you will actually see some of the magnesium hydroxide start to dissolve. First off, any questions on that? Do I need to get this down to an acidic pH to do that? The answer is no. You just need to drop it below that 10.46 number. You can still be basic in your pH and add some acid there, and you will still see your solid start to be more soluble because it is less than the baseline pH of that solution of 10.46. So you don't have to drop it. In fact, if you did this and you even dropped it into the nines, you would get a tremendously greater amount of that to be able to dissolve than it would be obviously at the 10.46. Any questions on that there? That is what it means up here when it says insoluble bases are soluble in acidic solutions, because what you're going to do basically is remove hydroxide from that solution by adding an acid, and that's going to cause the equilibrium to shift to the right and going to cause it to dissolve more. Now, what would happen in this case if I decided I want to increase the pH above 10.46? So if I wanted to increase the pH, I'm most likely going to add a base, right, to do that. And when I add a base, that is essentially adding hydroxide. Now, in this particular case, hydroxide is in the equation here. And in this situation, if I add more hydroxide, Le Chatelier's principle is going to tell us it's now going to shift. I'll make my big arrow there, away from the product side, and is going to shift to the reactant side, which in this case, the reactant side is solid. So if you actually brought the pH above 10.46, you're actually going to cause this guy to be less soluble. You're going to see more solid come out of solution in this case because the pH is affecting it. And again, this is the idea, like I said, in those qualitative analysis experiments where you kind of shift the pH around on some of these processes. And again, that's going to make it a pH environment where certain things will not come out of solution and certain things will come out of solution as you adjust it. Any questions on that there? Okay. So pH a really big factor in terms of solubility, just like common ion. And the third sort of factor that really affects solubility is concentration. Now, you could go by solubility rules, and solubility rules will tell you, hey, these two things come together, you should get a solid. And if your concentration of your ions are not correctly what it needs to be, you may actually not see that solid occur. It doesn't happen too much with you guys anymore with the qualitative analysis type of experiments that you do, but when you would do something like a general unknown qualitative analysis, like we talked a little bit about, where you have all the groups together and you just kind of go from one procedure to the next, every time you add your reagents, you're continuously diluting your sample. And if you're not careful with how much you add, you could get to an end test for one of those ions and it may not work out because you have the wrong concentration necessary. So what do we use for concentration? We do use that Q that we talked about earlier. So we can use Q and compare it to the KSP value to help us determine whether or not we would expect the precipitate to form. Once again, if Q is greater than the KSP, we would expect a solid to form. If Q is less than the KSP, again, we would not expect a solid to form. So let's take a look at an example here and kind of go through it and decide if we will get a solid forming or not. If we take 2 milliliters of a sodium hydroxide solution and we mix it with 1 liter of a 0.1 molar calcium chloride solution, we want to know whether or not we're going to get basically a solid that's going to form. The first thing you want to think about is your solubility rules and think about the ions that are floating around in that solution. You basically got some sodium ions floating around and hydroxide ions floating around in that solution. You also have some calcium ions floating around in that solution and some chloride. So based on solubility rules, that is an option of a solid that could form. Sodium is soluble in everything, which means it's not going to form a solid. And chloride is soluble in everything except for silver, lead, and mercury, which is obviously not in this mixture in this case. So your only option here is going to be calcium chloride or calcium hydroxide as a possible solid that may form in this particular case. So what that means is you do want to think about the KSP value for calcium hydroxide. So you want to kind of go and look it up there, maybe in the table, and find this value. And if you do so for calcium hydroxide, it is 8 times 10 to the minus 6. So in this particular case, this right here is going to be our only option of a possible solid forming, which will break apart into a calcium ion and a couple of hydroxides. Now, remember that we calculate Q the exact same way as we would calculate the KSP. So that means in this case, Q is equal to the concentration of calcium times the concentration of hydroxide. And again, we do need to square it. Now, we need to think about what we're doing, which is, in this particular case, we are taking 2 milliliters of our sodium hydroxide and we're dumping it in with 1 liter. I'm going to convert that into milliliters, the 1 liter, into 1,000 milliliters of our calcium chloride. We are mixing everybody together, which means we are actually doing a dilution, and we need to get the proper concentration of these ions when they're all mixed together. So the actual source of hydroxide is coming from the sodium hydroxide. That's the only thing that has hydroxide in it. So we need to do a little M1V1 equals M2V2 action. Our M1 is going to be our 0.2 molar. Our V1 is we're using 2 milliliters of it. We're looking for what its concentration is in the mixture. So we have 1,000 milliliters of the calcium chloride, again, converting the 1 liter into milliliters, and we got 2 milliliters of the other. That gives us a total volume of 1,002 milliliters, basically. So that would be our V2, which is 1,002 milliliters. Again, solving for M2 here, that's going to be 0.2 times 2 milliliters divided by 1,002. And that's a lot of zeros. So that's going to get us basically 3.99 times 10 to the minus 4 would be our hydroxide concentration in the mixture. Any questions on that there? Now, the only source of calcium is going to come from our calcium chloride, as that's the only thing that has calcium in it. And we would need to do a similar calculation for our calcium. So our calcium in this case, again, our M1 is 0.1 molar. Again, I'm going to use milliliters instead of liters here. So 1,000 milliliters is what we're using of it. Our M2 and our total volume here, when we mix it all together, 1,002 milliliters. That's going to give us 0.1 times 1,000 divided by 1,002. That's going to get us a M2 here of 9.98 times 10 to the minus 2. So again, it's important to make sure that you actually do get the proper concentrations of each of these ions in that solution. Now that you have it, you're good to go and plug it in here. So we're going to plug it into our Q, which is 9.98 times 10 to the minus 2. We're going to plug in our hydroxide, which is 3.99 times 10 to the minus 4. We're also going to square it as well. So that's going to get us here a Q value of 1.6 times 10 to the minus 8 in this case. First off, any questions on that? Now that we actually have the Q, we can compare it to the KSP value. So if we take a look at this here, our Q versus our KSP, and I kind of wrote on it, but I think that's a 6, I think I said there. And in this particular case, what we actually do see is Q is actually less than the KSP value in this particular case. And because Q is less than it, it's going to really go towards the product side. And as we know in this case, right, product side is all aqueous ions, which means we would not expect a precipitate to occur. And again, this is an example of, as I was talking about, that even though solubility rules will say when you put those two things together, you should get a solid. One major factor as to whether or not you actually see that is the concentration of those ions in that solution. And in this concentration of those ions, it is not the proper amount of each of those to actually make the solid form. So again, solubility rule is not 100% always correct. A lot of factors like the stuff that we talked about, common ion, pH, and concentration plays a really big role as to whether or not, for example, again, you'll see those things precipitate out or not precipitate out. Any questions on that there? The another aspect of KSP and useful aspect of KSP and something that really does sort of relate to the qualitative analysis experiments that you guys do is the idea of what is known as selective precipitation. And you could use KSP values to help you selectively precipitate out certain ions from solution and leave the other ones still in there. And that's really the whole idea behind qualitative analysis experiments is just that. We're just going to take out the ions we need at this moment and leave the other ones floating. And you could do that with the knowledge of the KSP. Why would that be helpful? Well, if we take a look at this example here, we have a solution that has basically bromide ions floating around and chloride ions basically floating around in this particular case. And we want to know what is the concentration of silver we would need to add to that to precipitate out only the bromide ions and leave the chloride guys still floating around in the solution by themselves. The reason we're using silver as a precipitating reagent is solubility rules, right? Bromide and chloride are soluble in everything except for silver, lead, and mercury. So something like silver nitrate, for example, would be a good reagent to use here as it would provide some silver. So the idea here is to add silver in the right amount that's going to take the bromide out as a solid, but leave our chloride still floating around. So how can we use the KSP to really help us do that and understand that? Well, we could write our KSP expression for silver bromide as we did earlier, and that is the silver concentration times the bromide concentration is equal to 7.7 times 10 to the minus 13. Now, the one thing that we do know about each of these ions that are floating around in the solution is we actually know the concentration of those ions that are floating around in the solution. So what we could simply do actually with the KSP expression is we could solve for the silver concentration, which would be 7.7 times 10 to the minus 13 divided by the bromide concentration. And again, we know that from the problem, and we could put it in there, and we will get 7.7 times 10 to the minus 13 divided by 0.02 molar. And if we do that, we will end up with basically 3.9 times 10 to the minus 11 molar. So what does that number represent? That number represents the minimum amount of silver concentration that you need to put into that beaker to actually start to see silver bromide coming out. Now, why do we have to sort of selectively precipitate these things out in the first place? The reason is right here. These are pictures of silver chloride and silver bromide. They essentially both make a white solid, which means if you just dumped in silver in there without thinking about it, you're going to get everybody to kind of precipitate out at the same time. And you can't really go, well, I think this little guy is like silver chloride is white solid. I think this is silver bromide. There's going to be no way for you to really know which one is which. Now, by doing this sort of selective precipitation, I know that as soon as I hit 3.9 times 10 to the minus 11, that is the minimum amount of silver I need to start to see the bromide come out of solution. So let's take a look at silver chloride and kind of do the same thing. If we take the KSP expression for silver chloride, silver times chloride equals 1.6 times 10 to the minus 10. Again, solving for silver, 1.6 times 10 to the minus 10 divided by our chloride concentration, 0.02, which was given to us in the problem. And that's going to get us here 1.6 to the minus 10 divided by 0.02, 8 times 10 to the minus 9 molar. What does that number represent? That number represents the minimum amount of silver you need to start to see silver chloride coming out. Yeah. Which one requires more silver to start to precipitate out? The silver chloride, right? You need a lot more silver chloride than you do the silver bromide. So if you want to precipitate out in this particular experiment just the silver bromide, you need to have at least 8 times 10, no, wrong number, 3.9 times 10 to the minus 11. Take a look at the right number would be good. There you go. You need to at least have our minimum amount for silver bromide, which is 3.9 times 10 to the minus 11 molar of silver. It's got to at least be greater than that, but it cannot be greater than 8.0 times 10 to the minus 9, because that is where we start to see silver chloride come out. So if you were doing this experiment, you would start with a concentration of silver that's greater than 3.9 times 10 to the minus 11, but less than 8.0 times 10 to the minus 9. And that will start to see white solid come out. And you can feel very confident that the white solid you see coming out is silver bromide. You could continue to add silver. You could even increase the concentration as long as you keep it below 8 times 10 to the minus 9. At some point, you probably will stop seeing solid come out. At that point, you could probably feel pretty confident that you precipitated out all the bromide ions. And now if you wanted the chloride to come out, you could then beef up the silver concentration to greater than 8 times 10 to the minus 9. You should start to see some more white solid come out. And at that point, you should feel very confident that that probably is silver chloride starting to precipitate out at this point. And you continue to precipitate them out. And again, you can selectively precipitate out each of these ions from each other by knowing the KSP and knowing the minimum concentration you need for your precipitating reagent to precipitate it out. As I mentioned before, if you're careless and you were doing this, and you just poured something in there at 8 times 10 to minus 9 or higher for the silver concentration, everybody's just going to come out at the same time, right? And you won't really know which one's which in this particular case. Any questions on that? And that's a really good aspect of KSP and a useful aspect of KSP when you're doing experiments like that where you want to selectively precipitate out. You can dial in, sort of the concentration of your precipitating reagents. And again, that's what allows certain ones to stay in solution and others to come out. Any questions on that there? And obviously, this is the part of the class that relates to those qualitative analysis experiments. And we talked about this previously. Again, there are these different groups of ions that are related to each other, not from the periodic table, but are related to each other based on solubility rules. Yeah. And again, there's our group 1 that you did previously after spring break is group 2. No, we don't do 2. Just got rid of it. We go group 3 next, I think, is where we're going, which is not bad. And she got rid of half of those as well, so there's not many in there left to go. So I think that is what's scheduled after spring break. And that is what you obviously look like as you're doing it. And we talked about group precipitating reagents as well. Flame test coming up in group 4, everybody's favorite. All right, well,